Okay.
Same rate as on each
Okay, guess we'll get started. We are the Knights who say me for message instantly. And our project is called Project Shrubbery. My name is Michael.
I'm Kevin.
I'm Aaron. Chris.
John.
Ryan.
Okay. And our project consisted of 3 parts. We had an RF transceiver, a VGA display, and a keyboard. So as I said before, the requirements were to receive and process a PS2 keyboard, both display the user and the received message on the VGA display, and transmit and receive between 2 Nexus boards with 24L101 transceiver chips.
Available from Spark Fun if you're interested.
So this is our system block diagram. The usual microblaze over here with the RAM, LMB, and these are all of our OTB slaves down here. So we have GPIOs for buttons. We have our interrupt over here, which comes from the keyboard, and we have LEDs, and we also have stuff to control the VGA monitor.
SPI for the wireless transceivers. So basically that's just a flow chart of what happens. You create the message, you press the button to enter or to transmit the message. It's sent over the wireless transceivers, it's received on the other end and displayed on the VGA monitor.
Alright, so the transceiver side of it was Michael and I's responsibility to take care of. Basically what happens is that the transceiver has operates around the 2.4 gigahertz range, and the way we've set it up is that there's a pipeline that's got 1 gigabyte wide, and basically we send a command into our transceiver saying we want to send this character. It gets packaged up with a lot of address bits, a preamble, and some cyclic redundancy checks on the end of it. Gets all dumped into a payload, which is then transmitted to the other side, ripped apart, and they find the byte we want to display, throws it up on the monitor, and then checks for another byte to come in. And as you create these bits, or as you create these bytes of data and send them over, we decided that it would be easier just to send them 1 byte at a time rather than to deal with a long single payload.
For the keyboard end, which was Ryan and I, basically when the keyboard button's pressed, a scan code is sent to the microblaze processor, and we read it from the FIFO, which clears that. If once it's released, it also sends an F0 and then the scan code again, which we ignore, and then we made a lookup table, and so it would just search through the first column of the lookup table to find the scan code and then see the character that was next to that. And then it's placed into a final string, which we can just cycle through to send.
For the VGA monitor, we wrote the HDL code to add an IP core to microblaze, and we used Digilent's code for the control signals for the VGA, the horizontal and vertical sync. And then we designed the characters pixel by pixel and set up an array in the VHDL code to output characters to the monitor.
So, integration and testing. So as we told you before, we kind of split this up into 3 parts. Each partner grouped in each part of this project. So the transceiver and receiver, which John we verified the SPI functionality by basically connecting the OC to the MISO and then making sure that it sent out the right information. And then we executed the right register, the read register, inside the 24L01 chip to make sure that it was getting the right commands. And then we set the switches to specific byte values, and then we were able to try to send that across, and then finally integrated the keyboard with the ASCII letters.
And for the keyboard, we just started by finding the baud rate, and that was just picking up the oscilloscope and measuring it. But we actually provided an access board, but we eventually found it. Then we then started by just pressing a single key and displaying that in binary on the LEDs, and then went from there by displaying full strings, and then went from there displaying on the actual LCD monitor.
And for the VGA, we coded all of our characters in VHDL, and what we had to do is say every time in X position and Y position in certain spots for the letter A, you had to light it up, and everything else would remain black. And so we integrated that VHDL data with the timing code provided by Digilant, and then we put both of those together into an IP core, which integrated into microblades. And then we integrated using microblade C coding to integrate the keyboard and the wireless.
Questions? How difficult was the integration?
All yesterday.
Everything worked by itself, and as we started adding together, they started creating like bugs with each other.
And so one of the things was like first we integrated the transceiver system, which was originally just sending switch bytes and displaying them to the opposite LED. And then we added that to the keyboard, and we were able to send individual characters and then strings of characters. And that went pretty smoothly. We got that up and running in about an hour or so, hour or two. And then we tried to integrate the VGA monitor, and it turns out that the VGA monitor was, you want to tell them about that?
Well, we turned the whole screen into like a matrix at first, so you could control any 8x8 spot on the screen and put a letter into it. But we ended up using 444% of our available slices. So needless to say, it didn't work. So we had to shrink down our available area to a smaller portion of the screen to be able to use our full font and control over it.
From my experience in the industry, that was difficult.
Yeah, it's just needed
You guys
more.
had a great experience.
Needed like more hardware for it.
We spent most of the integration stuff was the VGA team yelling at the rest of us to make more space for their program.
Yeah, we ended up changing our brand to 16K instead of 8K because we needed more time.
Pretty good.
So, let's go.
We have two setups. We have one on this side, one on that side to prove there's no wires connecting the two. You're welcome to come look at either screen, and you should be able to see both sides. So we decided that proper etiquette means you identify yourself first. You're going to notice that every message he sends is going to start with A space and then a message. So then Michael's pressing the buttons, and it should start showing up on this side.
Great.
And it's going to flash the identifier first and then show the message itself. So next, Ryan is going to create his own message with the identifier in front and transmit that back. You'll also notice that on the Nexus boards themselves, you see the little LEDs flashing. Those are, depending on whether you're transmitting or receiving, those are the physical ASCII characters that you're sending. If LED 6 is on by itself, it means you're in receive mode. If LED 8 turns on for a moment, it means you just switched over to transmit mode.
Still typing.
So he loves who?
What?
He loves who?
What? I love you.